Okay, so good evening everyone. Today, just like earlier sessions, I'll first start with the few questions that were left in the last session, and then I'll go to the theory part and then some problems based on that theory. Okay, so so let us start with this problem. So what it says is that suppose we have a sequence of measurable function and you have to prove that the set of the points where limit exists of that function, okay, that set is measurable. So for each x, so see fn is a sequence of measurable function on x, and corresponding to each point x, fn of x is a real sequence, right, for each x. Okay, and for all x in x, this fnx is a sequence of real number. Now what you have to prove, that the limit of these real sequences, the points at which it exists, that set we will consider, and then we have to prove that okay, this set will be measurable. Okay, so so before starting, so we know, so limit of any let's say this functions fnx, okay, this limit exists, okay, if and only if its limit inferior, lim and limit superior, lim sup, if both of the functions coincide, right, then we say that okay, this limit exists. Okay, so limit of fn exists if and only if lim inf of fnx is equal to lim sup of fnx. So this is
Okay, I found this on the web for fx. Okay, so this is, check it out.
Sorry for that. Okay, so this is what it means, that limit of fnx exists, right? Now you know one thing, that these functions, so suppose I am denoting this function as gx, let's say. So suppose this is my gx and this function is my hx, let's say. Okay, now you know both of these functions are measurable, right? Okay, so now these two things are equal is equivalent to saying that the difference is 0. So this means that g of x minus h of x is 0, right? But if g is infinity at x and hx is also infinity, in that case we cannot do so, right? So this difference, because in that case we'll have infinity minus infinity case, and we know infinity minus infinity does not make any sense, right? It's undefined. Okay, so we'll have to somehow remove that that case, right? So this is possible if h of x is finite, or maybe g of x is finite, any one, or g of x is finite. Okay, so so now let us, so these were the things what I'll be using, okay, this sort of thing. Okay, so let us see what this set is. So let us denote this set S as x belonging to x such that limit of fn of x exists. Okay, now this, as I have mentioned earlier, this will be nothing but x belonging to x such that, okay, so I will be denoting, so the same notation gx and hx. Okay, so such that gx minus h of x is 0, okay, intersection with x belonging to x such that h of x is finite. Okay, so we have considered the case where h of x is finite, so for that I am considering this one. So this is one. Okay, let me write it below, it would be better. Okay, so this is what I said just now, that we'll have to consider this difference when hx is finite. Okay, and the other case would be when both are infinity, because that is the only case which will create a problem. So union with x belonging to x such that g of x is equal to h of x is equal to infinity. Okay, so these are the all points of this set S. Okay, so I have rewritten it in this form. Now, so let me rewrite it again. So we know this is nothing but, I can write g minus h inverse of 0, right? So I am talking about this set, the first one. Okay, this one. This one is nothing but inverse image of, so if you want I can write it in this way, maybe g minus h of x equal to 0, right? So this is nothing but inverse image of 0. Okay, and this is being intersected with h inverse of, so it is finite, so h inverse of minus infinity comma infinity open, right? This will be the set. Okay, and then you have union, so this is one case. Okay, and then you have union with, so this is nothing but g inverse infinity. Okay, and then intersecting with h inverse of infinity. So this is another case, right? So where g, the points where g is also attained, just a second.
I didn't get that. Could you try again?
Okay, so what I was saying, that the points where gx and hx is infinity is this set, g inverse of infinity and h inverse of infinity, right? Now we know that this lim-in function and lim-su functions are measurable, right? So this will belong to the Lebesgue, the sigma algebra of Lebesgue measurable set. So let me see if I mentioned. So whenever I say this x, so this x is nothing but the measure space x, s and mu. Okay, so this is the measure space, underlying measure space. Okay, so this g inverse of infinity, this belong to s, this h inverse of infinity also belong to s. In the same way, this also belong to s, and this, okay, so we know when g is measurable, h is measurable, so the difference is also measurable. And since the difference is measurable, we have that this set is also measurable, and so this belong to s. Now since s is sigma algebra, we know that the whole quantity, okay, so it's better to denote this set by some other letter, say maybe a. Okay, so you don't get confused with this s. So this s represents the sigma algebra and this a is just the set. Okay, so from this we can say a belong to s, since s is sigma algebra, right? So what we got is that this set of points where the limit of the sequence fnx exists, that set is measurable. Okay, is this clear to you? This was just an easy exercise. I hope it's clear. Yeah. Do you have any doubt? The only maybe here you might get confused, so maybe you can just look at this part. If you are convinced, then it's fine, otherwise you can ask me.
Sir, I didn't understand how did you split that set A.
Which part?
The second step.
This one?
No, the upper one.
Okay, the upper one. Okay. So see what I was saying, that limit will exist if and only if the lim-in and lim-sup are same, right? Now why I am using this, because I know that lim-in and lim-sup functions are measurable. So now we can consider the difference of measurable function, right? Now this difference is also measurable, that we know. Okay, so when I write it in the form gx minus hx, okay, so this makes sense if and only if hx is finite, right? Otherwise, if I take the difference, suppose at some point x, okay, some point x naught, g of x naught is infinity and h of x naught is also infinity. In that case, I cannot do this subtraction. I cannot subtract h from g, right? This I cannot do. So just to remove this case, I have written this in two parts. So this set is being written in this union of two sets. Okay, so these are basically, moreover, these are disjoint, these two sets. Okay, so just look at this set. This set is just saying, considering this part, that gx minus hx is 0. Okay, and at the same time, when I am taking the difference, the hx should be finite. That's why I have taken intersection. Okay,
Okay, sir, I understood. Okay.
And the other case is when both are infinity.
Okay, sir.
Okay. Okay, if this is clear, then maybe we can proceed to the next question. So this is the other one. So what it says, that suppose you have a function f which is defined on this set x. Okay, so this is my x's. So this is my measurable space, and x can be written in this form as a union of two measurable set. Okay, so x is being written as union of two measurable set. Okay, now what you have to prove, so f is a function from x. Now x is just a union b. Okay, this is from, let's say it's r bar. I mean, r bar is basically r union plus minus infinity. Okay, so that's my extended real number system. Okay, so what this question is saying, that f is measurable on this set x if and only if the function f is measurable on a as well as measurable on b. Now I think I explained this in the last session, that what it means by measurable on a subset. Okay, so let me recall that. So see, when I say f is measurable on a, what it means, that suppose you consider this function g, okay, which is restriction of f on the set a. So this is a function from a to r bar. Okay, so now this a, again this a will be, instead of x I am talking about a, right? So instead of this x, it has been replaced by a. Now what does it mean when I say this function g is measurable? Okay, so let's forget about f for now. So this g is a function which is defined on a. Now this a is a proper subset of x. Okay, so this is proper subset of x, right? So what does it mean when I say this g is measurable, right? For x we know the definition, that g inverse of alpha comma infinity should belong to the measurable set S, so sigma algebra S, this one, right? So this means that g inverse, so g is measurable if and only if this g inverse of, let's say, alpha infinity, okay, this belong to, okay, so this g inverse of alpha infinity is a subset of x, right? So this is a subset of x. So what I mean, so let's say this is your x, from here this is your r bar, and you are considering on this a. So when you map this one, this is mapped somewhere here. Okay, now when you take the inverse image of this set, it need not be contained in a, it can be contained in this one, right? Because this need not be bijective. I am not saying this function f is bijective and all. Okay, so there might exist some other point, so it may be not one to one, so it can be many to one function. Okay, so here also something can lie in the inverse image. So this g inverse set need not be contained in a, right? It need not be. So for that, what we'll do, just to make it inside a, what I'll do, I'll just intersect with a. So this intersection should belong to this sigma algebra S. Okay, so if this is the case, we'll say that this g, function g, is measurable on a. Okay, so this is what it means by any function measurable on some subset of the given set x. Okay. Okay, so let's see the proof. So this was all about the theory part. Okay, so let us prove this part first. So this part means that assume f is measurable on x, and you have to show, so to show f is measurable on a and b. Okay, so so how you will prove? So okay, so instead of taking this minus infinity to, I mean this type of set, you can even deal with Borel sets, right? So so let us choose any Borel set from this Borel sigma algebra of R, the real line system, or R bar. So choose let E belong to B R bar, right? So any Borel set we are taking. So now what we'll look on? We'll look on the inverse image of that thing. Okay. So then F inverse of this E, okay, if I intersect this with A, okay, now what is A? F inverse of E, I can okay, so it was given to you, so from here only you can conclude. So see, this was what was given to you, that this set A and B are in the sigma algebra. So this A is in the sigma algebra, right? That is given to you. Now since F is measurable on X, okay, and this E we are choosing from the Borel sigma algebra, so this F inverse of E also belong to the sigma algebra, right? And this is because since F is measurable on X, and this was given to you that this belong to S, given. So overall what we can say, that this intersection belong to S, right? So let me write in another line. So this implies F inverse of E intersection with A, this belong to the sigma algebra S, just because it is a sigma algebra. Okay, in a similar way what you can show, that F inverse of B F inverse of E intersection with B, this also belong to the sigma algebra S, right? So so this implies that F is measurable on A, and this implies F is measurable on B. Okay, so I have done nothing special. What I am saying, we'll just try to follow this definition, measurable. Okay, so instead of this you can even choose any Borel sigma algebra, or even you can work with this also. I mean, it's not a problem. Instead of E you can choose this also, because these are the actually the sets which forms the Borel sigma algebra. Okay, so the Borel sigma algebra is generated by these sets. Okay. Okay, so instead of this E you can even work with this one, that's not a problem. Okay, so so what I have done, I have chosen a Borel sigma algebra, a Borel set, okay, this E, and I am looking at the inverse image of that set. So this is F inverse of E. I am intersecting with A, and I am checking whether that is in my sigma algebra or not. Okay, so I had to check this one, this part. Now for checking this part, what I did, so I know this A is given to us, that it belongs to the sigma algebra S. This F inverse of E also belongs to S because F is measurable, hence the intersection belongs to S. So this was just an easy check. We just used the definition and then concluded about measurability. Okay, so now let's check about the other way around. So what we'll do, so suppose okay, so is it clear, or is there any doubt? You can tell me if there is some confusion. Yeah, is there any doubt? Please respond if you have some doubt, you can tell me.
So clear for me.
Okay, clear to you. Okay, then let's move to the next part. Okay, so now what we'll do, we'll assume, suppose F is measurable on A and B both. Okay, so we'll assume that it's measurable on A as well as on B. So we will have to show that F is measurable on on X. Okay. Again we'll use the definition, or say the analogous thing what we have seen in the last sessions. Okay, so for that what we'll do, So to check measurability on X, we'll just choose a Borel set. So let E belong to the Borel sigma algebra, okay, and then we'll have to check this thing, that F inverse of E, whether that thing belongs to the sigma algebra S or not. Okay, that's all what I have to check. So what I can do, so this F inverse E, I can write it as F inverse E intersect with X, right? Because F inverse of E, so as I mentioned earlier, so this was my X, this was my, let's say, R bar, this E is something here, I mapped it here, okay, I am doing the other way around. So this E is something here, the Borel sigma algebra, I am taking the inverse image, so inverse image will be somewhere here, right? So F inverse of E, I can write it as F inverse of E intersection with X, and we know that X is nothing but A union B, right? Now I'll distribute it. So this F inverse of E intersect with A union this F inverse of E intersect with B, right? So this is just the distributive property. So I have distributed this intersection over the union. Okay. Now from the measurability condition of F, you know that this thing belong to S and this also belong to S, so the whole thing will belong to S, and hence F is measurable on X, right? Yeah, so whenever you can write X as the union of two sets, but both the sets should be in the sigma algebra, in that case checking measurability on X is equivalent to checking measurability on A and B. Okay. So let me know if you have any doubt or confusion. Okay, is everything fine?
Sir,
Yeah.
yes, sir, they are taking X as a union of A and B. So
Yeah.
it may be, it need not be disjoint.
No, I am nowhere using that it is disjoint. Have I used anywhere that they are disjoint?
No, sir. We have done 2 years that any measure space can be written as a disjoint union of a measurable space.
What any?
Sir, I didn't remember that.
Okay, so I mean, as far as this problem is concerned, so it is given to you that X can be written as union of two measurable sets. Okay, so it is given to you. This is something that have been given to you.
Okay, sir.
Okay, it's not something that you are, I mean, bringing it up. It's given to you that okay, X is given to be union of two measurable set, and then you have the question that function is measurable on X if and only if it is measurable on both the sets. Okay, so it's something like this is your X and you have been given that this is A and maybe this is, okay, so let's say this is your A and maybe this is your B. So this is given to you, this is the initial setup, and now the question is that checking measurability on the whole set X is equivalent to checking measurability on this A and on this B. Okay, so that was the question. Is that clear or is there some other confusion is there?
Yes, sir. Clear. But sir, like we are using the inverse image with intersection A. So
Yeah.
it may be also contained in B. It is also intersect with B.
No,
If they are not.
that's why I am intersecting it with A so that it is inside A. If I don't intersect, it may be in B. Okay, so that's why this definition makes sense. I mean, so this measurability of G, which is restriction of F on some set A, okay, that function is measurable if you take the inverse image. That inverse image can be in B, but I am intersecting with A and I am saying that this should belong to the sigma algebra. When this is there, then we say that the restriction function is also measurable.
Okay, sir.
Yeah?
Yes, sir.
Does that answer your question, or I mean?
Yes, sir. Clear, sir. I am thinking if B is contained in A, so the
Oh, B is
intersection will
contained in
also.
A. Oh, but then that doesn't make sense, right? So if what you are saying is very, very trivial thing. So when B is contained in A, so this union is nothing but A. So that means X is A, right?
Yes, sir. Okay, sir.
Right?
Yes, sir. Clear.
Okay. Okay, so this is the another problem. What I even wrote in the theory part as well. So when I was saying that what are the examples of measurable function, then I said that any continuous function is measurable, and there I mentioned that any monotone function if you take, that is also measurable. Okay, so before going to the proof, let's see how it is possible. Okay, so suppose this is graph of any function, okay, and that need to be monotone. So let us say that it's increasing, okay, for the moment. So it's like this maybe, okay. So maybe this is my x, okay. So this part, and then the function is like this, okay. This cannot be like this, but it should be increasing. So I'm saying this, and maybe this, maybe this, something like this, okay. Any random function I'm taking, okay. So this is defined everywhere, okay. So this is the function. Now what it says that if the function is monotone, then it is measurable. So for measurability, what we need to check, that this type of thing, that f inverse of alpha comma infinity, right? If I can, okay. So this is from R to R, that's why I'm saying this alpha infinity is open. So I have to check that this set should be measurable. If I can say that this belongs to the sigma algebra, or okay, here we are saying about Borel measurable, then this should belong to the Borel sigma algebra, right, generated by this, I mean Borel sigma algebra of real line, right? So I have to check. So this is to check, right, for measurability. Okay. So now what is this set? This set is saying that this is x such that f of x is greater than alpha. Okay, so let me choose any alpha. Okay, I'm choosing this as my alpha. Okay, so when I choose this as alpha, so the points where this function is greater than alpha, so these are the points, right? So this one, okay, I think it may not be visible to you, so let me choose. Okay, so this, everything, and so this is the functions. So this is the fx greater than alpha, and corresponding to that, the interval what I am getting is from here to infinity. So this is alpha, so f inverse alpha maybe. So this is f inverse of alpha, this point. So so from this picture, okay, at least for this picture, it's clear that when I say fx greater than alpha, it is nothing but f inverse of alpha comma infinity. I mean, okay, so I should not say, maybe, I mean, okay, this part will be open for sure, but this may be closed or open. So I'll give two examples, okay. So I'm not, so it's clear that either it will be like this or it will be like this, right? So I'll give you example with this. So in this case, you can see that this set fx greater than alpha, in this case what will be happening, so it will be open, right? So it will be open because this is continuity is there at this point. So I mean, if I say that the points which are greater than this function, because at f inverse alpha the function is taking the value alpha, right? So that's why this will be the case. Suppose this is my alpha, okay. So suppose this is my alpha, okay. So I am not saying this will be f inverse alpha, this is not a correct way of saying, but for this case, yeah. So the main question is whether it will be open from the left end or not, okay. So when I say this is my alpha, okay, the orange point, so the function, the fx which is greater than alpha is again this line, right? So this one, this one and this one, right? And correspondingly the interval will be this closed one, right? So here this closed and then continuing, right? So because at this point the function is taking the value this one, so let's say this is x alpha, let's say, okay? So then it's saying in this case it will be x alpha comma infinity, right? Now is this clear? I mean, it's not f inverse of alpha, but it's some point x alpha, okay? And this will be closed interval. So in this case, let's say this is my x alpha, okay? So it's better to write x alpha, okay? So this is my x alpha, okay? Now I think it should be clear. So let me make this gray. Is this fine? I mean, pictorially what I'm trying to say? I'll give the proof, but this is the proof. Actually, this is the proof. It's just that I'll have to write in mathematical form. That's it. Is this figure clear to you, or should I repeat? I mean, you can tell what to do. Should I repeat this, or is it fine to you?
It's clear, sir.
Okay. So if it's clear, then let's proceed to the mathematical part. Okay. So so as in this case, let us assume, so without loss of generality, okay, assume that, so let us assume that f is increasing. So let us assume f is increasing, okay? In that case so my claim is, okay, so what I proved here, I'm saying that any inverse image of this type is an interval, and we know interval is in the Borel sigma algebra, right? Any open set, any closed set is in the Borel sigma algebra. So all this, in both the cases, it is in the Borel sigma algebra of R, okay? And hence this function is measurable, okay? So claim is that f inverse of alpha comma infinity belong to the Borel sigma algebra R, okay? So I mean, you can even take this also, okay? That is not a problem, but okay. So let us deal with this. So let me prove this one, okay? So one proof what I gave you, that this pictorially, okay? So that I'll mimic that only. So it's basically, you can prove in two ways. So one, which is this pictorially, I'll write that proof first. So what you do, so this is your f inverse of alpha comma infinity, okay? So this is nothing but x such that fx is greater than alpha, right? So let us take x alpha to be infimum of x belonging to R such that f of x is greater than alpha. So this is what I was saying, that here what this is exactly what we do. We were taking the list, I mean the infimum and of these values, right? So I mean pictorially I was explaining you here, and this is the mathematical thing, that okay, we will take the infimum of all such point where the function is taking value greater than alpha, okay? So so as I've shown you here, so this f inverse of alpha comma infinity will either be this x alpha comma infinity, or it will be closed x alpha comma infinity, right, as I have explained here. But so this is one proof. So we know that both are open set, okay, open or closed interval. So this belong to the sigma, so Borel sigma algebra of real number, okay? Other proof is, so this is the first proof, okay? So maybe this is the first proof. The other proof is, I mean, the most obvious one. I mean, you don't have to think much about that proof. So what you can do, so this is my claim, okay? So let me put it here only. The claim would be that I will not bother about whether it's closed interval or open interval. What I'll say that f inverse of alpha comma infinity is an interval. Okay, I'll prove this one. Okay, so how we can prove this one? So what is the property of interval? Interval means that if you choose 2 points, any point which is lying between these points will belong to that set, right? So interval, so S is an interval if for any x comma y belonging to S such that x is less than y. Okay, and okay, let's take Z also. If for any x comma y comma z belonging to S, not like this. Okay, for any x comma y belonging to S, x less than y, and for all z which is lying in this set, so which x z belonging to x y implies z belong to S. So what it means that you choose two real number. So this is, let's say this is your set S. Okay, so maybe I cannot draw the interval. So okay, let's say this is your set S. So what it says, it is not an interval, right? Why? Because if you choose 1 point here, 1 point here, this point is not lying in the set. If this is, I mean, if this is the figure, then obviously all the points which is lying between these 2 points, all the real number which is lying between these 2 points are in the set S. Okay, so that is the definition of interval. If you recall, maybe the interval AB is denoted by x belonging to R such that A less than x less than B. So all points lying between A and B are in this set. Okay, so that is the mainly the definition. Okay, so I'll try to prove that one, and that is quite easy. So what you do, so let x comma y, okay, belong to this f inverse of alpha comma infinity, right? So this means f of x is greater than alpha, f of y is greater than alpha. Okay, now without loss of generality, you can assume either x is greater or y is greater. So without loss of generality, assume x is less than y. Okay, now let z belong to R such that x is less than z less than y. Okay, so what we have chosen any in between function, in between point. Now we know that the function f is monotone, so this would imply fx less than equal to f of z less than equal to f of y, right? Just because it is monotone. Now we know that this fx is greater than alpha, so this would imply f of z is greater than alpha, and then this would imply that z belong to this set f inverse of alpha comma infinity, right? So what it says, that this proves that this is an interval, and since it is an interval, it is in the Borel sigma algebra. Okay, now whatever, whether it's closed interval or open interval, whatever it is, we can say that it is a Borel, it belongs to the Borel sigma algebra. So in interval, and hence Borel set. So is this clear? Do you have any doubt, or is this fine?
Yes.
Okay. Okay, so this was all the 3 questions that were left. That were left in the last session. So let us proceed to the next part, which is the theory part. Okay, so you have seen so far, in this week, that how to define the integration of functions. Okay, so you started with the first thing, what you started with, integrating the simple functions. Moreover, it is non-negative. Okay, so what is simple function? The first thing. So you have seen that the simple function, okay, so let me not write x. This is simply this type of function, I equal to 1 to n alpha I, and then the characteristic function of ai. So what it means, it is basically taking value alpha I on the sets ai. So it is piecewise constant function. right? So in the set ai it is taking value alpha I, that's the only thing, right? So this is some way, this is constant function but in each of the intervals, so it's piecewise constant. Okay, so you can say it's piecewise constant. Okay. So these are the functions which we call simple function. Okay, now so maybe I'll show you an example, maybe pictorial example to explain how this simple function can be represented in the same different form, right? So so let us see here. So if you take this function, okay, so this is, let's say this is taking value this, and then here maybe this, and then let's say again here you take the value this. Okay, so let's say this is alpha 1, this is alpha 2, okay, and the corresponding sets, let's say this is E1 or A1, so since anything A1, and then here this is your A2 and this is your A3. Okay, so these three intervals to choose, and then this is the function. Okay, so this is one function what you have. Okay, now so this is one representation. Okay, so paste. Okay, so here, okay, if I want to write in this format, what will be the representation? This will be phi is equal to where should I write? Okay, maybe here only. So this phi is equal to summation I equal to 1 to 3 alpha I and then characteristic function of ai, right? Where and here what is, so in a1 it is alpha 1, in a2 it is alpha 2, this point, and in a3 it's again alpha 1, so here alpha 3 is equal to alpha 1. So this is one representation what you have of simple functions, right? Okay. Yeah, in the similar way, instead of taking this set a1, you can even do partitions like this, right? So maybe I'll just write it here. Okay, so what I was saying, that instead of taking this a1 a2, now I'll partition it in a bit different way. So I can choose this as my b1, let's say this is my b2, and maybe again let's say this as b3 and this as b4. Okay, so here what I can say, this phi is summation alpha I chi of bi, and I is varying from 1 to 4, right? What I have done here, the sets were totally disjoint, but here I am taking, I mean here also it's disjoint, but I have partitioned a1 in two parts. Okay, so in this situation this alpha 1 is equal to alpha 2, right? Because so it's what this is, so this is alpha 1 chi b1 plus alpha 2 chi b2 plus alpha 3 chi b3 plus alpha 4 chi b4, right? Now in this b1 and b2 it's the same value alpha 1, so this alpha 2, so let me write in beta 1 format, then it might be good. So beta 2, so this is beta 3. Okay, so let me write this beta I, and then this is beta 4, right? So you know this beta 1 and beta 2 are exactly the same, so this is equal to alpha 1, this is also equal to alpha 1, beta 3 is alpha 2, and beta 4 is again alpha 1, right? So here beta 1 is equal to beta 2 is equal to beta 4, and all these are alpha 1, and beta 3 is alpha 2, right? So this is another way of representing the same function. Okay, and you can even represent in one more way. Okay, so far what you have seen, that all these beta bi's or ai's all are disjoint, right? That is the one thing what you have noticed so far, that all are disjoint. Now let us see once again what could be the other possibility. Okay, yeah, so Okay, so now you can maybe, so now what you do, so let's say this is my C1, okay, and this is my, let's say, C2. So this is my C1 and this is my C2, okay, and I'm writing my phi function as gamma I chi of Ci, right? So this is my way of writing this function. I is equal to 1 to 2, okay. Yeah, so this is my gamma I. So let me rewrite it, okay. So if I call this as my, so this was my A1, this was my A2, and this was my A3, right? So if I take some point from here, okay, so phi at x, where x is in my A1, okay, so when it is there, it's taking value alpha 1, but when this x is in this A2, this is taking alpha 2, and when x is in this A3, it is taking value alpha 1 again. But if you compare with this one, okay, what it's saying, that if you choose point from here, it is taking value gamma 1, okay, so maybe slash, and here it's saying in this region it is taking value gamma 1 plus gamma 2, right? Because this, if I choose this point x, so instead of writing A1 A2 A3, let me write in this fashion, that would be more clear, I guess. So this is I am saying this is C1 minus C2, and this is C1 intersection C2, and this is C2 minus C1, okay. So these are the three sets, right? So if you notice, if I take the point from C1 minus C2, it is taking value alpha 1. If I am taking from the intersection, it is taking value alpha 2. If I am taking from C2 minus C1, it is taking value alpha 1, right? And now if I compare it with this thing, so it is taking value gamma 1. I mean, if I take from here gamma 1, and this is gamma 1 plus gamma 2, and this is gamma 2, right? In C2 it is taking value gamma 2. I mean, I hope this is clear, right? Is this fine?
Yes, sir.
Okay, so the main question is that, okay, if I have same representation, I mean different representation of the same function, okay, then what will be the integral, how to define the integral, that is the question, okay, that how to define the integral of the function which can be represented in these three different forms, okay. So now you have seen, so what we can do basically, so given any function, from this picture you can see that given any function, you can write this as disjoint summation. So suppose initially you have been given this alpha I chi of ai, so if these are not disjoint, if this ai's are not disjoint, you can make them disjoint, right, using this type of thing. So you can always make this as summation beta I chi of bi I, so this was from I equal to 1 to, let's say, n1, you can make it I from 1 to n2, such that these bi's are disjoint. This you can always do, right? The same way how you can see it here, that C1 minus C2, C1 intersection C2. So this is just for 2 sets, but you can do the same thing for n sets, okay. In that sense, when you are able to, I mean, write this in the form of disjoint set, now you don't need to do anything. So suppose, without loss of generality, that this phi can be represented in this form where these ai's are disjoint. And then it's quite simple. In that sense, then, okay, so one more thing, that this alpha I are positive, okay, greater than equal to 0. Why we need to do this, it will be clear from here. Then this phi will be summation alpha I mu of ai, okay, I equal to 1 to, say, n1. So why we need to consider this non-negative thing? Because suppose alpha 1 is positive but alpha 2 is negative, and mu of a1 is also infinity, mu of a2 is also infinity. In that case, it will create a situation of infinity minus infinity, So just to remove that thing, we take non-negative functions, I mean non-negative constant. So this is the first step. To define integration, this is the first step, that what integration means for a piecewise constant function. Okay, we know for constant function integration is nothing but the value and the measure of the set, right? So if the graph of function is like this, then we know that the integral of f is the area which is covered under this curve, which is this is the height, this is the f of, I mean whatever this is, alpha 1 or alpha, and this is, I mean the size. So in case of real line, this is the length of the interval. In abstract setting, this is the measure of the set E alpha, right? This is what I said in, so E alpha is nothing but f inverse of this alpha. So for constant function we define in this way, and for piecewise constant function we define in a similar way, we extend it. Okay, so this is the very first step to develop the theory of integration. Okay, so at the first step we got how to define the integration of piecewise constant function, non-negative piecewise constant function, or non-negative simple function. Okay, then okay, so this is what I have explained to ignore infinity minus infinity case. Okay, so this is why we need to start for integration for non-negative functions. Okay, now the next question is how to define integral on subsets. So far I have told you about this integration on the whole space X. Okay, so now the question is how to define integration on some subset E. Okay, so suppose this is my function phi, which is summation alpha I chi of ei. Okay, and then I'm saying just integrate this phi on some set E. Okay, now E is measurable. Okay, so this E is measurable and all EIs are measurable because I'm talking phi is measurable function. Okay, so this integration of phi on the set E is nothing but the integration of phi on the set X, but you just multiply with this characteristic function, right? So this multiplying with characteristic function makes it 0 outside the set E. So on E complement it is 0, so the integration remains same. Now this is nothing but, so this is X and this is summation alpha I chi of ei, and then you have chi of E. Okay, now the product of two characteristic function, okay, is nothing but this intersection of these two space. Okay, so do you know this thing, that product of chi of A into chi of B will be chi of A intersection B? I mean this is quite obvious, because suppose you choose some point from A, in that case, and which is not in B. Okay, in that case this chi of B will be 0, right? And the same will be holding for the intersection, because since it is not in B, so this will be 0, it will not be in the intersection. And now again, if you do the other way around, that if you choose a point which is in B but which is not in A, in that case this will be 0, and since it is not in A, it is not in the intersection, again it will be 0. The moment you choose a point in the intersection, this will be 1, and since it is in the intersection, it will be in A, it will be in B, so both these things will turn out to be 1, and hence the product of 1 will be 1, and here also we have 1. So product of characteristic function is again a characteristic function of the intersection. Okay, okay. So this will be this integration of this simple function. So this is your now new function I equal to 1 to, let's say, n, to 1 to n. Okay, so this is your new simple function, and again, so as I have explained, since suppose EIs were disjoint, then this is also disjoint, so the integration will be nothing but summation I equal to 1 to n alpha I and mu of EI intersection with E. I mean just using the definition, right? So this was my definition, so using that as my definition, I am getting this alpha I and the measures of this set. Okay, I hope this is fine, right? Or is there any doubt?
Sir,
Yeah.
Sir, the integral of the simple function over e is equal to the integral of phi over x.
Okay.
Did not
This
get
one,
it.
this one. Are you talking about this one?
Yes, yes.
Yeah. So what? So see, what I'm saying that suppose this is your x. I'm talking. So I mean, for the simplicity, suppose you are in the real line. So suppose this is your sum set. This is your x. Okay, and this is your a. Okay. Now what I'm saying, you have to integrate this function phi on this. Okay, let's say e. Okay, so you have to integrate this function on this set. So suppose this is your function and you have to integrate on this region. Okay, so what it means, integrating over e means over here the integration is 0, I can say. So I can write this plus 0 function on e complement. Yeah.
Yes, sir.
Okay, so this is what I can write. Now if you see this side, this is nothing but what it says, that it is taking the value phi, because this characteristic function is 1 when the x is in the e, and it is 0 when x is not in e. So when it is not in e, so I can write this e. So let me write it here. So this function phi chi e complement is x, I can write it as phi chi e plus phi chi e complement, right? I can break the integral in two parts. That I can always do, right? On e and e complement. Now on this e complement, this is 0, right? Because this chi of e is taking value 0. So this whole function is 0 on e complement, right?
Yes, sir. Yes, sir.
So I can, so that's why I mean this is there. Okay. 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 So this is done. Now, so there is one property which says that if this function phi1 is less than equal to function phi2, then the integration of phi1 is less than is equal to integration of phi2, maybe on x or on any subset e. Okay. So this is there. That is called the monotone property of the integral. So this is true for the non-negative functions, obviously. So far, so today I think the most of things will be for the non-negative function. Okay, for today's session, I guess. Okay, so these are the few properties of the integration. I mean the basic properties basically for the integration of simple functions. Now let us go to the integration of any non-negative measurable function. Okay, so you have seen one theorem that if you have any non-negative measurable function, then it can be approximated using simple function, right? So what was the theorem? The theorem was that if you have any function f which is measurable, this implies there exists a sequence phi n which is of simple function. The sequence is of simple function such that this phi n increases to f. Increases means that this phi1 less than equal to phi2 less than equal to phi3 and so on, it keeps on like this, right? So it increases to the function f, and this is true for all the points. So phi1 of x, so this is for all x, so this is true for all x. Okay, so this is the theorem what you have seen in the earlier sessions, right? So okay, let me keep it here but in a better shape maybe, fingers such that this phi1 less than equal to phi2. Okay, so that's why when you want to make sense of integration of f, we will be using the integration of the simple function. So this is how we define. So this is the definition, that integration of this function f will be the supremum of all the simple functions phi, okay, which is bounded by f, and that's it. I mean taking supremum of the integral of phi where phi is less than equal to f. Okay, so this is how, and the reason being this one. So from this theorem we know, so this implies that the phi n is less than equal to integral of f. Okay, and so because of this reason we are taking this condition phi less than equal to f, I mean from here, and we are taking supremum just because it is less than equal to the integral of f. So let's take the supremum to reach to the integral of f. That is the main idea, that you choose all the simple function which is less than equal to f, take the integration and then take the supremum, define it as the integral of function f. Okay, so this is the motivation to define the integral in this way. Okay, I hope the motivation is clear to you. Yeah, is this fine? Is there any confusion here at this point?
Yes.
Okay. Okay, if this is fine, then okay, this is just a comment that the measure what you take, the definition of integral will change. So I'll give two examples. I think that was given in the lecture as well. So I'll just repeat that to make you understand that how the measure is playing role in the integration, right? So it's not just the usual integration what we see, the Riemann integral. So you'll see how it is different. So changing the measure will change the value of the integration totally. Okay, so so when you take this mu to be the Lebesgue measure, this integration is called Lebesgue integration of f. Okay. Okay, and this is the same, what I hinted you earlier, that for any subset E, this integration of f will be nothing but integration of f multiplied with the characteristic function of E. Okay, so that's it. And these are the few properties. So this is the monotone property, which says that if g is less than equal to f, then the integration of g is less than equal to integration of f. So in the whole discussion I will be talking about non-negative functions. Okay, so all these are greater than equal to 0. So when g is less than equal to f, the integration of g is less than equal to integration of f. Okay. So you have seen similar sort of thing in Riemann integration also. Okay, it's exactly the same property, that when two functions are non-negative, the Riemann integration of the the smallest function will be less than equal to the Riemann integral of the greater function. Okay, so this f is greater than g here, so the integration is also greater than this. So this is just the monotone property of this integration. So it's true in the abstract sense as well. And when E and F are measurable such that E is contained in F, so then in that case the integration of f is less than equal to integration of f. So always this f is greater than equal to 0, otherwise this they need not be true. Okay. Okay, so and then this is again another property which says that if you multiply the function by c, then this c can be taken out of the integration. That's it. So this c is again, this is also greater than equal to 0. Okay, although this is true for C in R as well, but since we don't know the meaning of this integration for non-positive function, that's why we have restricted just to C greater than equal to 0. Okay, so these are the few basic things, and this again, this integration of sum of two function is equal to the sum of E integration of the functions. So this is there. And okay, so these are something which I think you have not seen earlier. This you have seen, that if the function is identically 0, then the integration on any set will be 0. Okay, but even instead of taking this, if you have f is equal to 0 almost everywhere on E, okay, that on the set where it is not 0 is of measure 0, in that case also this integration will be 0. Okay, so you don't need 0 everywhere. Okay. Okay, and then okay, so I think you can think about this thing from the example, this one, f of x, this example 0 when x belong to q and 1 when x belong to q complement. I told you there that this is not Riemann integrable. That you can obviously check, because when you take any partition, just because of the density of rationals and irrationals in the real line, the upper sum will be 1 and the lower Darboux sum will be 0. So they will never match. But it is because see, this q is countable, so this I can say that f is equal to Okay, so let me do it other way around. Okay, 1 and 0. So it says that f is 0 almost everywhere, because the place where the points where the function is taking non-zero value is the set of rational number, and we know that the measure of set of rational number is 0. So that is why this function f is 0 almost everywhere, and that is why the integration of f over the real line is equal to 0. Okay, so I mean, this is just the example of where f is not identically 0, but it is 0 almost everywhere. Okay. Okay, the next property is saying that if you take integration over some set E, which is null set, that is the measure of that set is 0, then in that case also the integration is 0. So either the function is almost everywhere 0, or the set over which we are integrating, that is null set. In both the situation the integration is 0. Okay, now if integration is 0, what can you say about the function? Okay, so here also f is greater than equal to 0. Okay, so when the integration of this is 0, in that case you can conclude that the function is 0 almost everywhere. Okay, so you might be thinking that we can also say that the measure of x is it's 0, but you cannot conclude from here, because if the function is 0 almost everywhere, the measure of the set E need not be 0, right? So what I am saying, that this is basically the converse of E, the point E. Okay, so what I am saying, suppose this was given to you, so from here can you conclude that the measure of x is 0? No, you cannot do. This is not even true, right? This is not true. I can give you an example where the measure space, obviously you can take f identically equal to 0. So this example, if you take this, integration of function is 0, but the measure of r is infinite, so you cannot conclude this one. Okay, so this is not true. Okay, but the converse of f is not true, but the converse of E is true. So this is true, the converse part of E. Okay, so now you can define further measures using the integration. Okay, what you can do, so suppose you have this function phi, which is simple function. So for example, let us consider this point only. Okay, this one, that phi is simple function, measurable simple function. You can define a measure mu of E to be integration of phi over with this given measure mu. So this function nu is also a measure. Okay, so and it is defined for all the sigma algebra. So initially, okay, I have written it here. So this was your measure space with the measure mu. Using this measure mu and the function phi, you are defining a new function which is nu in this way. This new function nu is also a measure, and it is defined on the same sigma algebra S. Okay, so mu, if you remember this, what does this mean? Mu is a function from S to 0 infinity, and here also this nu is a function from S to 0 infinity. Okay. Okay, and it can be further generalized, so you don't have to restrict just to the simple function. If you choose any non-negative measurable function f, you can define a new measure nu. So nu of E is equal to integration of f with respect to the measure mu over the set E, and this is again a measure. Okay, and further you can even prove that integration of any function with respect to this measure. Okay, so this is the another measure what we have defined. Okay, so integration of the function g with this measure nu is equal to integrating this product of these two functions with respect to the earlier measure mu. Okay, so this is with respect to the earlier measure, and this is the the newer one, the measure nu. Okay, so these are the certain properties, and in short form it is written in this way: d of nu is equal to f d of mu. Okay, Okay, so these are the few theorems. So the monotone convergence theorem, which says that if you have a measure space and if you have a sequence of increasing non-negative measurable function, so it is non-negative measurable function and it is increasing. Okay, and the sequence f(x) converges to some function x. In that case, you can say that the integral also converges to the integral of f. So in short form, what it says, fn, let's say fn increasing and fn converges to f implies integral of fn converges to integral of f. Okay, and point, the only thing that need to be noted is that this fn is non-negative. Okay, so that is also important. So non-negative. Okay, then so again, as I said in the very first session, that convergence of function does not imply the convergence of Riemann integration. I gave one example also using this the function, this one, right? So I constructed a function fn. I showed that the function fn converges to this one, but the integral were not converging, right? Even the limit function was not integrable, Riemann integrable. But this is true here when the functions here are increasing. Okay, some newer version will be, I mean, some better theorem will be, I think you'll see in the next session. For today, you just restrict to this one, that then the function's sequence of function is increasing and it is converging to some function f, then the integration will also converge. So this basically means, okay, if I want to write in other way, that the integration and the limit can be interchanged. So it says that the limit of fn is equal to limit of fn, okay, which is f here, right? So this is the limit of fn is f. So it says that the function, the integration and the limit can be interchanged. Okay. Okay, so this was about this monotone convergence theorem, and as an example you can see this one. So in this one here, you saw that the integration of sum of two function is equal to the sum of integration of the functions. So you can generalize this to n number of functions. So using induction, you can prove that integration of f1 plus till fn is nothing but integration of f1 plus integration of fn. So that can be generalized. But what about infinite? If I take infinite functions, okay, so this, using monotone convergence theorem, you can prove this one. That's okay. So forget about this one. I mean, don't need to forget, but just focus on this part. So what it says, that the integration of infinite sum of this non-negative measurable function is equal to summing the integration of each of the functions. Okay, and this can be proved using monotone convergence theorem, and it's quite easy, right? So you just need to consider the sequence fk k equal to 1 to n. Now these are increasing and these are bounded by this summation k equal to 1 to infinity fk. So using the monotone convergence theorem, since these are non-negative, these are increasing and it is converging to this function, you will get this one. Okay, so it's quite, this proof is quite simple using monotone convergence theorem. Okay. Okay, now let us talk about another important theorem, which is Fatou's lemma. Okay, so okay, I think in the lectures you must have seen that this Fatou's lemma is proved using this monotone convergence theorem, but you can do the other way around also. So assume Fatou's lemma and prove monotone convergence theorem. Okay, so that I think is mentioned here in some sense. Okay, so let us see what Fatou's lemma says. So it says that if you have a sequence of non-negative measurable function, then this inequality is true. Okay, so it says that this limit infimum, so here we are not saying that the fn converges to f. Here we are just saying that we have a sequence of functions of measurable function. That's it. We are not saying that it is converging, it is increasing or whatever. We are not putting more restriction. We are just saying that if we have a sequence of function, then this liminf of fn, integration of that will be less than equal to liminf of integration of fn. Okay, So this is what it says. Okay, so here again we have assumed that the functions fn are non-negative. Okay, so that is important. Now using this you can prove this. Okay, again this is very easy to prove. So what it says, so it is nothing but, in some sense it is the monotone convergence theorem but with less restrictions. Okay, so what it says, it does not say that the function fn are increasing. What it says that the function fn is bounded by fx. So it is not saying that f1 is less than equal to f2. Okay, so let me state it what it says. So suppose we have a sequence of functions fn which are non-negative, again non-negative, okay, extended real valued function, measurable functions. Assume that this fn is bounded by f, okay, and this function fn converges to f. So here we are not saying that fn are increasing. Okay, that is the only, but you can put it here. I mean, if you want, you can put it here to prove monotone convergence theorem. But we are dealing with much lesser restriction. Then you can prove that limit of fn is equal to the function, the integration of the function. So here also the result is similar to what we have seen in the monotone convergence theorem. Okay, so how to prove this? So it can be proved very easily. I mean, it does not require much tool, but the only Fatu's lemma. So from Fatu's lemma we know that x lim inf, okay, so let me use another color. So lim inf of fn is less than equal to lim inf of fn. This we know, right? And what is lim inf of fn? Since the function fn is converging to f, this is nothing but integration of f, right? So integration of f is less than equal to lim inf of integration of fn, right? So this is what we have. Now what you can do here, so you have to prove, so this I can say less than equal to limit of fn, right? Because lim inf is less than equal to the limit, so I can do that as well. Okay, what else I can do? So this is there. Okay, so this let us put it here. Now we also have that this fn is less than equal to fx, right? So from here I can say that fn is less than equal to integration of f, and again if I take limit, so limit of fn is less than equal to f, and comparing these two I can say that these two are equal. So here I have used the Fatu's lemma, and here I have used this condition. Okay, so the proof is quite simple. I mean, when you assume Fatu's lemma, it's quite simple. Okay, okay, so this is, okay, maybe I should keep it here. So okay, yeah, okay, fine. So okay, so it is actually a stronger version of, I mean, monotone convergence theorem. Here you do not need to assume that the functions are increasing. Okay, so you just have to say that the function is bounded, it is non-negative, and this measurable function, that's it, and the function fn converges to f. So fn converging to f implies the integration fn converges to integration f. Okay, okay, now so here we have assumed that it's non-negative, right? So why non-negative is important? So let us consider this function minus 1 by n in the interval n comma 2n and 0 elsewhere. When I consider this function, now calculate what is, so this function, can you tell me where it converges? This function fn converges to, can you tell me? So for each x in R, this function fnx converges to 0. And what is the integral of the function fn over whole R? So this is just minus 1 by n, and the difference is n, so it is minus 1, right? I mean, I am talking about the Lebesgue integration. So Lebesgue integration for this function will be the same as the Riemann integration. Anyway, so this integration of fn is minus 1 and the integration of f is 0, right? So because this is my f, the limit function, so you can clearly see that lim inf of this integral fn is minus 1 and this side is 0. So it is saying 0 less than equal to minus 1, which is not true, right? Was I too fast? Maybe you can think a bit. So this fn converges to 0. So lim inf is equal to the limit because this is convergent series sequence. So this part will be 0. This function is 0. So the integration is 0. But here this integration of fn is minus 1. So the limit, I mean, it's just a constant sequence, minus 1. So the lim inf of this will be minus 1. So we'll get this inequality, which is false. So that is why the above theorem is not true for the if the function is not non-negative. Okay, so here the function is non-positive, so it is less than equal to 0. Okay, so this is one thing. Now if you see here, I mean, this inequality, this can be equal for someone and it is strictly less than for some function. As example, you can consider this one. So fn is non-positive, so minus of fn, this is non-negative, right? Okay, again this is measurable. If you, so minus of fn is nothing but plus of this, so minus of fn, right? Then minus of fn, this will be, the right hand side will be plus 1 and the left hand side will be 0. So 0 strictly less than 1, right? So this is an example which says that the equality in this need not be true. I mean, it is strict inequality. I mean, for some function it can be equal, but it is not equal for all the functions. That's all it says. So this is just an example which shows that in Fatu's lemma, strict inequality can hold. Okay, so is this fine?
Yes, sir.
Okay, so now let us move. Okay, so here I have shown you that this Fatu's lemma is true for non-negative function. Now the next question would be, what can we say something for non-positive function? So as in case of this example, so what can we say? What sort of inequality can we give? Okay, so this is a theorem for the non-positive function. What it says, that suppose fn is a sequence of non-positive function, then lim sup of fn is greater than equal to, I mean, integration of lim sup of fn is greater than equal to lim sup of integration of fn. And the proof is quite simple, right? So you know that this fn is non-positive, so minus of fn is non-negative, right? Now you apply Fatu's lemma. So if you apply Fatu's lemma, what it says, that lim inf of minus of fn is less than equal to lim inf of minus of fn, right? This is what it says. Now this lim inf of minus fn is nothing but lim sup of fn with minus sign, and this is lim sup of minus lim sup of integration fn. Okay, now when you multiply with minus sign, so it will be plus, and then the inequality will be reversed. So this is by Fatu's lemma. So it's nothing, I mean, you just have to use Fatu's lemma for minus fn and you will get this one. Okay, so this is just an obvious implication of the Fatu's lemma. Okay. So this is for non-positive function. So far I have not defined what is measurable function. Okay, I mean, sorry, integration of a general measurable function. But suppose it is given to you, I mean, I think you have seen the lectures as well. I'll define at last, but as of now you just assume this, that okay, what is the notion of integration of any measurable function. So here this function, I'm not talking about non-negative function, but any measurable function is there. What do you mean by integrability, and if it is integrable, how to define that? Okay, so that is a different thing. So assume that okay, you know the integration of a function. Okay? Assuming that these are the few, I mean, extension of Fatu's lemma. Okay, so this is called reverse Fatu's lemma. What it says, that suppose you have a sequence of function. okay, measurable function, and if there exists a non-negative function g which is integrable. So far integrable means assume that g is finite, integration of g is finite, okay, and what this is I will explain at the last. Okay. So this is what it means by integrable. The function g is integrable. So it's given that you have a sequence of measurable function and there exists a non-negative, okay, so it's a typo, integrable t, integrable function on x such that, so the sequence of function is bounded by this g, okay, then you have to prove that lim sup of fn is greater than equal to lim sup of this integral of fn. Now it's quite simple. So okay, the proofs are very easy. So what you can do, so this fn is less than equal to g means fn minus g is less than equal to 0. Okay, one more thing you can ask that why can we subtract this g, okay, because g can take the value infinity. So in one of the exercises and that I'll discuss, I'll show you that when this integral of g is finite, okay, that means the function g is integrable. In that case, the points where the function gx takes the value infinity is of measure 0. So it is a null set, okay. So since it is a null set, I can forget about that, because as far as the integration is concerned, I don't need to bother about the null sets, okay. So what I'm saying, let me write it here. So suppose x I have to integrate over f, so I can write e plus e complement. Now suppose this e is a null set, so this integration will be nothing but 0, so it will not be contributing in the integration. So that is why I can ignore the set of measure 0, okay. So since it is given to you that the function f is integrable, okay, so it is integrable, so this integration of g is finite, so this implies g is finite almost everywhere, okay. So that's why I can make this difference, okay. Is this clear to you? I mean, this I will show, this part I will show you maybe today itself, okay. So this I will show. So okay, so this fn minus g is less than equal to 0, so you can use this lemma. So for non-positive function, so it says that lim sup of fn minus g is greater than equal to lim sup of fn minus g, right? Now you can break the integration, okay. So I am leaving the proof, but you can easily derive it, it's not a big deal, okay. So you can derive it by your own, I mean, just using this. So maybe I should leave this one, but okay, so I will not discuss the proof, but you can derive it simply using the Fatou's lemma. In similar way, so this is another result. What it says that suppose you have a sequence of functions, measurable function, and suppose again you have an integrable function such that fn is, I mean, lower bounded. Here we have that fn is less than equal to some function. Here I am saying fn is greater than equal to some minus of g. In this case, I will have fn plus g greater than equal to 0, okay. So I will use Fatou's lemma for this one, okay. I will use Fatou's lemma for this one to deduce this one in a similar way, okay. Okay, so these are the something which is in some sense extension of the Fatou's lemma, okay, which deals with more general function. So the above two theorems were just for the non-negative measurable function, but this is for any measurable function, okay. Okay, so this is few example of the integration. So this is one of the example, I think. So have you seen these things? I mean, I hope you have seen. So if you will tell me, then I will repeat, otherwise I will skip. So you know that when we are dealing with the counting measure on the power set of natural number, so the integration is nothing but the summation, and when you are dealing with the Dirac measure, integration is nothing but the evaluation of the function at that point. So do you need this explanation, or should I mean, skip this one? You tell me what to do. Yeah, you can tell your individual preferences, then I can do proceed. What do you say, Sri Lakshmi?
Sir, actually, I didn't see the video.
Oh, okay. Then in that case, it will be useful. Okay. So, okay. Then I'll explain you. So, okay. So see. So what I'm saying, that suppose you have a set of this x is the natural number, and this is the sigma algebra power set of n. Okay. And the measure what we are taking here is the natural measure, which is the counting measure, because for the natural number set, counting measure makes sense, that you are counting the numbers. Okay. So what I'm saying, that the integration of any non-negative function will be nothing but the summation of the values of the function. Okay. So how to prove that? So maybe I can write here, I guess. Okay. So this is for a part. Okay. So suppose this fn, so consider this function fn. Okay. So far, if you want to evaluate the integral, the definition is given using the simple functions, right? This is all you have. So we will have to take help of simple functions, and then the maybe monotone convergence theorem, because that deals with that one, right? So the definition says that you have to take supremum, okay, of simple functions, and monotone convergence theorem says that you don't need to take the supremum, you just need to take the limit, right, if it is an increasing sequence. So if this, and we know that any function, measurable function, can be approximated using simple function in an increasing fashion. So you just need to consider the limit of these simple functions. Okay. So the main goal is to find what this phi n will be, which approximates the function f. Okay. So this is how we will try to find the expression for the integration. Okay. So suppose this fn is a function from natural number to this real number, or the positive real number, because it's non-negative, such that fn of k, okay, is equal to f of k if k is less than equal to n, and 0 if k is greater than n. So what it says, that okay, so the graph of f is, let's say, at 1 2 3 so on. So at 1, let's say it is taking value this, at 2 it's taking value this, at 3 it's taking value this, at 4 it's taking value this. So now when I will define f1 is that at 1 it will take the value 1, and the rest point it will take the value 0. So this is my f1. f2 will be that at 1 it will take the value 1, at 2 it will take the value 2, and the rest point it will be 0. Okay. So this is the function. So you can clearly see it is a simple function. So for the natural number, this is the constant function, right? It's just like the characteristic function. Okay. So these are the simple function what we are taking here, and these are measurable function, you can check. So measurable simple function. Okay. So now this you can clearly see that fn is increasing, and it increases to f, right, just by the definition. And that is why this integration of f will be equal to the limit of integration of fn by monotone convergence theorem. So this is by MCT. So by MCT, right? Okay. So MCT implies that integration of f is nothing but the limit of integral of fn. Okay. So now what is the integration of fn? So let us take this integration of fn. So fn function, if I integrate, it is a simple function, right? So this is something like f characteristic with this function, this set. So this is the set 1 2 till n, right? fx times characteristic function of this. So what is this? So just notice. Okay. So if you take x from these of the sets 1 to n, it will be f of x. If it is outside, then this will be 0. Okay. And x is nothing but n, right? So n not k. So if you choose any number from this one, it will give the value 1, and the function will take the value k, fk, right? And if it is outside this set, then this will be 0. Okay. So integral of fn is this one, integration of f over the whole natural number, right? And then this is nothing but f of k, and the measure of this set. Okay. So if you rewrite this, so let me rewrite this one. So this is f chi of 1 mm, so this is like this one. So summation f1, sorry, fk and chi of singleton k, right? This is the expression of the simple function. So I'm writing this in terms of simple function k equal to 1 to n, right? So instead of writing this, you can just write in this way, that if k is equal to 1, then this is fk f1 and chi of 1 will be 1. So okay, so I hope you are understanding this. This is nothing but, so let me write in this one, f1 chi of 1 plus f2. So what I am doing, I am just breaking it into simple functions, I mean the piecewise constant function, chi of 3 and this so on, right? So if you take any point x in one of this set, this will be giving f1, f2 or f3, whatever it is. Okay, so this is the expression for the functions, and the integration of this will be nothing but f of k and measure of the singleton k, right? And this is measure of this set is 1, right? And this is summation is there. So this is nothing but summation k equal to 1 to n f of k. Okay, so the integration of fn is turning out to be summation k equal to 1 to n f of k, and when you take the limit n going to infinity, this will be the summation, because this is the positive series, I mean series of positive real number. Is this clear, or do you have any doubt? Can you respond a bit quickly?
It's clear, sir.
Okay, so this was about this function, and for this one I will not do, I'll just give you a hint. Okay, so what you can do, you choose any simple function, okay, phi, and then for simple function you see what this is coming, okay, and then for each measurable function you will have a sequence of function which will converge to that function. So here also I did the same thing, right? For a simple function I am seeing how this integral is behaving. So I saw that, okay, for simple function it is behaving in this way. In the same way you check that for any simple function d of delta x naught, this is phi of x naught for phi simple, and then use the approximation and MCT to deduce this to get star. Okay, so it's just 2 steps. So this maybe you can check. Okay, now I'll just explain what integrable function is, and that's it. So integrable function, so suppose you take a measurable function, you know that the measurable function can be written in f plus and f minus, right? And you know that this f plus is non-negative, this f minus is also non-negative. So the integration, I mean you can define integration for these two quantities. So you know how to, I mean, get this f plus and f minus, you know, because these are non-negative, and you know how to integrate non-negative measurable function, right? Okay, so now the point is, what will be the integration of f? Okay, so suppose you define integration of f as this one. Okay, suppose this is the definition. Now the problem is that f minus can be infinity, right? And even this can be infinity. In that case, what will be the integration of f? In that case, it cannot be defined, right? So that is why we have to restrict the set of integrable function. I mean, not all measurable function can be integrated. So there will be certain function which cannot be integrated, while certain can be. Okay, so that's why we need to define what do we mean by integrable function. Okay, so integrable function means, so this is the definition, that a function, measurable function f, will be called integrable if integration of mod f. Now what is integration of mod f? So mod f I can write at f plus f minus, so this is f plus f minus. Now this always makes sense, because f plus is, I mean, even if it is infinity, even if this is infinity, it does not create any problem, because f plus and f minus both are non-negative, so it cannot take negative values, so there will be no ambiguity in defining so. So we know that integration of mod f is always makes sense. So it will be called integrable if this integration is finite. Okay, now actually to make sense of this integration, you just need to assume that this should be finite. If this is finite, then you are done, right? Even if you assume, okay, so because this is finite, then there will be no infinity minus infinity case. Okay, but why we are taking this as the definition? I mean, why to take with mod f? Because ultimately, okay, because when you will go to the LP spaces later on, you will see that this is a norm. So this is L1 norm of f is nothing but mod of f. Okay, so that's why we take this as the definition for integrability. Okay, so that's the only reason. Otherwise, to make sense of this integration, you just need to be sure that this is finite. Okay, okay, so this is called the, I mean, this is, if this condition is satisfied, we say the function f is integrable, and when when it is integrable, the integration is defined in this way. So integration of f is nothing but difference of integration of f plus and f minus. Okay, in the same way you can define integration for complex valued, and complex valued function will be integrable, and you can define it in this way. So when f is equal to u plus iv, right, so real part and imaginary part, then integration of f is integration of real part and plus iota times integration of imaginary part. Okay, so I mean, that is just the natural choice to define the integration. And these are the properties that, so again, this linear combination of two integrable function is integrable, and this is the usual thing that scalar multiple will come outside, and summation you can write as the sum of two integral is equal to the, so this actually, this is nothing but combination of two things. F plus g is equal to integral of f plus integral of g, and integration of cf is c times integration of f. So if you combine these two things, you will get this one. Okay, so this is nothing very non-trivial thing. Okay, so this is one of the property. The second property, you have seen this for Riemann integration also, that mod of integration of f is less than equal to integration of mod of f. So this is there, I mean, this property. Okay, so this was about the lecture.
Sir,
Yeah.
in the definition part, why are we considering just integral of f minus as finite? Why are we not considering about f plus finite?
No, when I am saying this integrability, this means that, so when I say this mod of f is finite, so what does this mean? This means that f plus f minus is finite. This means that this is also finite, this is also finite, right?
Yes, sir. So actually we are assuming integral over x f minus dm as finite.
Mod of f.
In the bracket.
This one, okay. Oh, okay, this one. So this I mentioned, okay. Okay, you are saying that why to consider this one?
Actually, we need to consider both,
No, why?
Over x f minus as well as.
No, suppose I assume that this is finite. Suppose for the moment that this integral is finite, right? Then this definition makes sense, right? I am saying
Okay,
that this definition should make sense. The only problem is when infinity minus infinity case arises. So I am removing that part. Then this will make sense. I am saying that the way how we are defining will make sense. But this is not the definition. I am saying to define integration of f, if we restrict this one, then that is enough to give meaning to this definition. Okay. So this enough is for this definition. Okay. But this is not the definition. For the definition, we assume that both should be finite. Okay, so I understood the confusion. So you understood what I am saying, that to give sense to this quantity.
No, sir.
Oh, you didn't get? No, I am saying that, see, the definition says that both should be finite. Okay, that is the definition.
Yes, sir. Okay.
Now I am saying that to make sense of this quantity is sensible. I mean, this definition, so this definition is sensible if we, so this quantity is not definition, this quantity is sensible if we assume integration of f minus to be finite, because there will be no infinity minus infinity case. Okay, but to define the integrability I am using this mod of f is finite. Okay, and the reason being that in later on you will see that integrability, okay, so integrability will mean that this integration is finite. Okay, this is called or mod of, so in L1 space you will see that this integration is finite, and for that we need this as well as this to be finite. Okay, and that is why this mod definition is there. Okay, so just to make this as a meaningful space, I mean the Banach space, and the norm will be this one. Okay, so I mean this will be, as of now if you look it at this point you can say that okay, so if I have been given this, so f equal to 1 let's say on R, then integration of f I'll say it is infinity. If I want to define the notion of integration I can say this, right? It is a constant function, so it should be, it is infinity.
Yeah.
But that will not be in L1 space. Okay, so you will see later on what is L1 and LP
Yes, sir.
spaces. So that's what I wanted to say there. Okay. Okay, so now let us do at least one exercises today. Okay, so let me see what I can do. Okay, this, all are interesting, but okay. So I have used this one in today's lecture, so I will prove this problem. I will solve this one. Okay, so let us start the solution. Okay, so what it says, that suppose that integration of f is finite. Okay, so we are dealing with non-negative measurable function. Okay. So suppose that integration of f is finite, you have to prove, to show that the set E1, let's say, that x belonging to x such that f of x is infinity, you have to prove that this is null set. Okay, so this is the first thing what you need to show. The second thing is that E2 such that x belong to x such that f of x is greater than 0. Okay, greater than 0 means it is, I mean it is greater than 0 and it is less than infinity. Okay, so this is sigma finite. Okay, so let us start with 1. Okay, so what you have been done, so it's better to understand first graphically. Okay, and if you understand then you can write also. So suppose this is your function f. Okay, I mean let us draw some graph. So okay, so maybe something like this. Okay, so this, and this is the part. So let's say this is my E1. E1 is the point where the function is taking value infinity, so it's not on the real line, so I am leaving this part. Okay, so here f is in this region, f is equal to infinity. Okay, now suppose this is there. So okay, so what I'll do, I'll construct a sequence of simple function, okay, that will be less than equal to f, and again using the monotone convergence theorem I'll have to, I'll say that okay, something I'll use, but the point is that I will use this condition, that integration of f is finite. Okay, and I'll use simple function which is less than equal to the function f. Okay, so let us start with this one. Suppose this is my phi1. Okay, so phi1 is taking value 1 here and elsewhere it's 0. Okay, phi2 is the taking value 2 in this interval and rest where it is 0. So you can clearly see that phi k is less than equal to f, right? Because here it is, the function is infinity and these are finite, and at these points since the function f is non-negative, so f, this phi are always less than equal to function f, because this is strictly greater than 0 and this is equal to 0 in this region, this one. Okay, so in this region the phi k's are 0 while the function f is positive, and in this region the function is infinity, so obviously this f phi k's are less than equal to f. Now this implies, so the reason being why we are using simple function, because we know what is the integration of simple function. That is the only reason. Okay, so if I integrate this phi k, okay, so this integration is less than equal to f by monotone property of the integration, and this f, okay, so phi k is also greater than equal to 0. Now this integration of f is finite. Okay, that is the main point. So what is integration of phi k? Integration of phi k will be nothing but it is taking value k. So let us take k outside, and it is characteristic function of e. So phi k is equal to, so let me write it here, phi k is equal to k times characteristic function of e, or e1, right? So phi k is in k times characteristic function of e1, and this is less than equal to integration of f, and this is finite, and this is nothing but k times measure of e1, and this is, so okay, so this is less than equal to f. Now if mu of e1, so suppose mu of e1 is not 0, that is mu of e1 is positive, right? Measure is always greater than equal to 0. So this implies that mu k is less than equal to integration of f upon mu of e1, right? Since it is not 0, I can take it here, and this is something constant. So this is, so constant, some constant, this is also constant, right? So the right hand side is some constant m, right? It is, and this is true for all k, right? This is for all k in natural number. So this is a contradiction, right? This is saying that the set of natural number is bounded, but this is not true, right? So this is a contradiction. So therefore mu of e1 is equal to 0. Okay, so that is the proof. Okay, is there any doubt? I hope you understood this construction.
It's clear, sir.
Okay, so now let's go to the second part. The second part says that e2 is x belonging to x such that f of x is greater than 0. Now this is equivalent to, so I can write it as x, so I will use this short notation, okay, to denote this. So this is saying 0 less than f less than 1, union 1 less than equal to f less than 2, union 2 less than equal to f less than 3, and so on, right? I can write it in this way. Combiningly I can write it as 0 less than f less than 1. So sigma finite means you have to write it as a union of sets such that the measure of each set will be finite, right? So if you don't forget the definition, so E is said to be sigma finite if you can write E as ei, I equal to 1 to infinity, such that mu of ei is finite. Okay, so what I am trying to do, I am trying to write this E2 as a union of some sets, and I will show that each of the set is of finite measure. Okay, that is the goal. Okay, so combiningly I can write this as this way. So union of n less than equal to f less than n plus 1, okay, where n is from 1 to infinity. Okay, I can further rewrite this set in this way. So union n from 1 to infinity 1 by n plus 1 less than equal to f less than 1 by n, right? And then union with this one. So okay, so the union with u n equal to 1 to infinity. I mean this I am just partitioning it up, okay, and again I will have to take help of simple functions, so that I will show how. So so far I have just tried to write this E2 as a union of some sets. My goal would be to show that these sets, the set of this from this and this, is of finite measure, and again I will use the help of this thing, that integration of f is finite. Okay, okay, so now let me construct. So again, I mean, so maybe I can explain better in terms of figure. So let me draw a figure quickly. So suppose this is your function, maybe this sort of function, anything. Now suppose this is 1, this is 2, this is 3, okay, just for example. So let me say this, let's say this is half, so this is half, this is 1 by 3, and so on, right? So this one. So what I have said here, so how I have partitioned this, so this says the function f taking value n to n plus 1. So this is one set, right? This is one of the set, so you understand, right? So this is 2 less than equal to f less than 3, okay, and this is the set 1 less than equal to f less than 2. I mean here it's hollow and here it's, I mean not here but in this part. So I mean not here, basically I'm writing it wrong, so it's basically here, so it's here corresponding. So these are the points where the function x such that 2 less than equal to f less than fx is strictly less than 3, okay. So this is 2, it's taking equal to 2, so this is the set, and for this one this is the set, okay. So these are the sets what I mean for this special type, I mean this graph of this function, okay. So now what I'll do, I'll construct simple function. How I'll construct, so in this region, in this set I will construct function of this sort. So it is like this, okay. Here I mean I'm taking the lowest value, right? So what I have done, I have partitioned the range. I mean this is how you, I mean as I was mentioning in the last session also, that how you approximate the measurable function using simple functions. Similar type of construction you use. So what I'm doing, I have partitioned the range in a proper way and I'm defining some simple functions, okay. So how this simple function is like this one. So in this one I'm taking the lowest value, okay. So and in this interval I'm taking the lowest value, and so on, right? So this here I'm considering these sets, I mean in this region, okay. So it will go on, okay, like this, okay, and these are quite clear, these are this. So let me write it what these functions are. So suppose what I'm doing, I'm defining phi of x, so it's better to name them. So what I can do, so let me name this as what should I name? So these I'm saying it's b, so just because of 0 I'm putting 0 here, and this is n, okay, these sets, and so it is basically union of b0 n is from 1 to infinity, and this I am saying this okay, let me write denote by cn. So this is union of cn, so it's so just remove 0 also, so it's just right b of n, these are my, or a of n, and let's say a of n, and these are b of n from 1 to infinity, okay. So this is my bn and these are my ans, okay. So now I have to show that the measure of an and measure of bn are finite, okay. So I have constructed this functions phi, I will define this. So phi is nothing but phi of x is equal to the function 1 by n plus 1 and the characteristic of this b of n, okay. So in this, so these are my, in this picture this is my a2, right, and this is my a1, sorry b1, this is b2, this is b1, and this is my a1, okay, and this is my a2, I mean this is smaller part, so this is my a2, okay, I mean in this picture, okay. So this is my, I am taking the lowest value, and in the set bn, here also I will take the lowest value n and chi of bn, here it's an, okay. So this is the simple function, and you can clearly see that this orange line is always less than equal to the blue line. So this is always less than equal to f, and this is always greater than equal to 0, right? Now if I integrate it, so 0 less than equal to 1, so this is summation. Since these are simple functions, so 1 by, not simple, it is infinite sum, but you can use MCT and all those things. Oh, so you have seen this also, so that is good enough. So integration of summation of fn is equal to summation of integration. So I am using that. So this is mu of an, okay, and this is summation n mu of bn, n equal to 1 to infinity, and this is less than equal to integration of f, and this is finite. That is the most important thing. Now the moment I say that this is finite, this integration, this means that all these summations are finite, right? And that is why each of these measure of these sets must be finite, must be bounded, because if it is unbounded, if this sequence, so these are sequence of real number, right? Mu of bn is nothing but measure of the set bn, which is a positive real number, again non-negative real number, again with this one also. So these are real sequences, okay? And in fact in this case you can clearly see, that summation of 1 by n alpha is finite if and only if alpha is strictly greater than 1, right? So this mu of bn must be of the form 1 by n 1 plus alpha, so that this n cancels with this one. That summation of n is equal to infinity, right? So it must be of the form, not must be, but if you take mu of bn to be 1 by n squared, let's say, then you know that n will cancel, then summation. So if I take mu of bn to be 1 by n, in that case also this summation will be 1 by n, this quantity, and this is infinity, this is divergent, right, this summation. So that's why, so actually we can say much more, that it's not just finite, but it will have a certain form, so that the summation is finite. So from here what we can conclude, so from here what I should write is summation n from 1 to infinity 1 by n plus 1 mu of an, and summation n mu of bn is finite. Both are finite. In particular, mu of an, this should be bounded. So this is finite. Mu of bn is also finite. In fact, it will be bounded. Okay, so this is all good enough for our case. So we showed that you can write the, so what we showed that this E2 can be written in form of union of such set, such that measure of each of the set is finite. Okay, so we can say, so this implies E2 is sigma finite. Okay, then maybe the rest of the question you can think. Okay, so this is quite interesting. That monotone convergence theorem is true for increasing function, but it is not true for decreasing function. But it will be true under one assumption, which is this one, that if you have a sequence of non-negative decreasing function, and if you assume that integration of the first function is finite, then this will hold true, that integration of fn will converge to integration of f. Okay, it's similar to what you have seen when dealing with this increasing sequence of sets. So you remember this type of thing, that continuity from above and continuity from below, that en is equal to limit of mu of en. This is always true, right? But when you deal with the intersection, you need to assume that mu of em is finite for some m. In particular, you assume mu of e1 is finite. Similar sort of thing is here, that you have to assume that integral of f1 is finite. Okay, and in fact you can even remove this one by saying that integral of fm is finite for some m belonging to natural number. If this is also there, then it's fine. So this is true under this condition. Okay, so it's similar to what you have seen for the sets. Okay, so you can try this one, I mean this part, and here at least you can solve this one. This is just to find a counter example. Okay, so you think on these problems. Okay, and okay, this one is also, it's not that difficult. This also you can do. Okay, this one is also easy only. So what it says that if you integration of, so what it says is just that integration of fn on x converges to integration of f on x, then you can show that integration of fn on any measurable set e converges to integration of f on many measurable set e when fn converges to f. So that is given to you, and this is given to you, then that would imply this is true, but under the condition that this is finite, I mean this integral of f should be finite. Okay, okay, and you can find a counter example when this is the case, this will not hold. Okay, so maybe I'll discuss this in the next session. So for now I think this is enough. So if you have any doubt, you can ask now. So do you have any doubt?